Hello class, welcome to the 2.1 part 2 lesson. So we're going to continue our discussion on parallel lines, and more specifically we're going to actually elaborate, we're going to actually prove the theorems or postulate or the theorems that we mentioned in the first part, which has as it relates to the corresponding angles theorem, same side interior angles postulate. So we'll be talking about those and using them in proofs. So again, our essential question and learning goals are the same as in the first part, as well as the vocab. So again, let's recap what we mentioned about angle pair postulates and theorems. So we have a pair of parallel lines, N and M, cut by a transversal T. And we mentioned that we mentioned the same side interior angle postulate. Remember that a postulate is generally something that we take as true. We generally don't prove postulates, generally speaking, because it's more of a statement that we take as true. So in this example, 3 and 5 are examples of same side interior angles, and we know that by the postulate that it says that they add up to 180, so we know that they're supplementary. Another example of this would be, for example, angles 4 and 6. They would be same side interior angles as well. For alternate interior angles, this is actually a theorem, and that we'll prove today. Angle 3 and angle 6 are equal to each other, are congruent by the theorem. Same for angle 4 and 5. Now for the corresponding angle theorem, again another theorem that we'll actually prove. 3 and 7 are examples of corresponding angles, and we said that they're congruent. 4 and 8 are also examples of corresponding angles, and those will also be congruent, as well as 2 and 6, or 1 and 5. Alternate exterior angle theorem. We will not, this will be something that you'll have to prove, but we will not do that in this video. You guys will do that as an exercise, but we will prove these other two. And it turns out we'll prove these using the postulate for the same side interior angle postulate. And so an example would be angle 2 and angle 7 would be exterior, and so they're also congruent. Another example would be angle 1 and angle 8. Those are also congruent by the alternate exterior angle theorem. So let's go ahead and prove the alternate interior angles theorem. For that, the postulate that we mentioned earlier, the same side interior angles postulate, is something that we take as true. Therefore, we can use that in order to prove the alternate interior angles theorem. So looking at this diagram, we have two parallel lines, M and N, cut by a transversal. We'll call it T. And we're looking at just 3 angles here. So given that M is parallel to N, this parallel symbol, prove that angle 1 is actually congruent to angle 2. All right, so we're going to do a 2-column proof for this. Remember that the given statement is number 1, and the reason is that it's given. It's when you're doing a proof. Now for the second statement, what we're going to do is we're going to be using the same side interior angles postulate for this. So we know by the same side interior angles postulate that angle 1 and angle 3 are same side interior angles. So we know that these two are same side interior angles, and so they have to be supplementary. So we're going to say that angle 1 and angle 3 are supplementary. And that's given by the same side interior angles postulate. And because they're supplementary, that means that they add up to 180 degrees. So that's going to be our next statement. That angle 1 plus the measure of angle 3 is equal to 180 degrees. And so for our reason, well, the reason for that is the definition, that is what it means to be supplementary. The definition of supplementary angles is that they add up to 180. And so we'll say that this is the definition of supplementary angles. Okay, so that's what it means to be supplementary, and we got that statement in equation format. Now what we're going to do is we're going to look at another set of angles. This time we're interested in angles 2 and 3. So it turns out angles 2 and 3, here and here, they form what we call a linear pair. And so therefore they are supplementary and they add up to 180 degrees. Remember that they're a linear pair because they're formed by the intersection of these two lines here, and they're right next to each other, or which we call adjacent. So they are actually supplementary. And so we're going to use that, and we're going to say that the measure of angle 2 plus the measure of angle 3 is also equal to 180. And the reason for that is, well, there's a couple of reasons that you could state. You could state that angle 2 plus angle 3 is 180, and that's an angle addition postulate because you're adding two angles together. But you can also say that we're using the linear pairs theorem, which is more specific. So I'm going to say both of these. I'm going to say angle addition postulate, but really we're also using the linear pairs theorem. Okay, so linear, some people say the linear pair postulate, but I'm just going to say the linear pairs theorem from the book. Okay, so that's the linear pairs theorem that states that they add up to 180 degrees, they're supplementary. And so now we have those two equations, and so we know that since they're both equal to 180 degrees, that means that they have to be equal to each other. And so we're going to set them equal to each other. So we have something that looks like that. Measure of angle 1 plus measure of angle 3 equals angles 2 plus angles 3. So now that we have them equal to each other, what's the reason for that? Well, the reason for that is that you can consider it a substitution where you have 180 equals 180, and then we know that angle 1 and angle 3 equals 180, so we can replace it. Or you can call it a transitive property. Remember that transitive property states that if A equals B and B equals C, then A equals C. You can also think of it as a transitive property. So I'm going to call it substitution or really transitive property. I prefer call it the transitive property. Okay, so these are two different properties, by the way. Substitution property would be if you think of this as being 180 equals 180, and substituting that for, you know, this left side and substituting this for this left side. Those are two different things, but you get to the same result either way. And so I'm going to say just use transitive property for this one. All right, so for step 6, since we know that they're equal to each other, then we also know that we can solve, because we can actually solve for this because we have 3 on both sides. And so if we cancel it out, we're just left with angle 1 equals angle 2. And so we're going to cancel this angle 3 out by really subtracting it on both sides. So what we're going to be doing is we're going to be subtracting the measure of angle 3 on both sides. And when we do that, it goes away. It kind of cancels. And so what we're doing is we're using the subtraction property. We call it the subtraction property of equality. And that property states that if you're subtracting the same number on both sides of the equal sign, well, if you subtract it on one side, you got to do it on the other side. And that's the subtraction property. And so we're left with measure of angle 1 has to equal the measure of angle 2 because the 3 cancels out. And so now we have angle 1 equals angle 2. We're almost there. We're trying to show that it's congruent. Well, we know that if the measures are equal, then they have to be congruent, right? So we know that this is the same thing as saying angle 1 is congruent to angle 2. And that's because that's the definition of congruence. That's what it means to be congruent. Congruent means that they're the same measure. And so we can say that the reason that we did that is that this is the definition of congruent angles. All right, and that concludes our proof of the theorem that we were looking at, which was the alternate interior angles theorem. So now let's look at the other theorem, the corresponding angles theorem. So how do we go about proving this? Well, first off, we're given the two parallel lines cut by the transversal, and we want to prove that 1 and 2 are corresponding angles. Well, we want to prove that they're congruent to each other, which means that we'll have to prove the corresponding angles theorem. All right, so let's set up the two-column chart here. So we know that the two lines M and N are parallel, and the reason is that it was given in the problem. So let's start with our second statement. So for our second statement, we know that from the same side interior angles postulate that 2 and 3 are actually angles 2 and angle 3 are actually the same side interior angles, and they add up to 180. So we're going to go ahead and say that they're supplementary, kind of like what we did in the previous problem. So angle 2 and angle 3 are supplementary. And the reason is that this is from the same side interior angles postulate. All right, so for the third step here, so now we know that they're supplementary. We know that they have to add up to 180. So we're going to go ahead and write that out. They add up to 180 because that's what it means to be supplementary. So we're going to say that that's the definition of supplementary angles. All right, so now we're on step 4. So now we're going to use information. We're going to need information about angle 1 here. Okay, so angle 1 and angle 3. We're going to have to tie in together angle 1 and angle 3 together. And so what we're going to say is that, kind of like we did in the other problem, angle 1 and angle 3 actually add up to 180 degrees because they form a linear pair. Okay, and that's called the linear pairs theorem, okay, or angle addition postulate for 1 and 3. So we're going to say that the angle 1 plus angle, if you add together the measures of angle 1 and 3, you're going to get 180. And we're going to just call that the linear pairs theorem slash angle addition postulate. Okay, so angle addition postulate. All right. And so now for step 5, since now we know that they add up to 180, then since they're both equal to 180, we're going to set them equal to each other. So we know that the left side, angle 2 and angle 3, has to be equal to angle 1 and angle 3 because they're both equal to the same thing, which is 180. And so we're going to say that the left side of step 3 is equal to the left side of step 4. And we'll call that the transitive property, just like we did in the previous problem. And so now if we cancel out the measure of angle 3, in this case we're subtracting the measure of angle 3 on both sides, and it cancels, so that's the subtraction property. And then you'll end up getting that angle 2 is equal to angle 1. And so this is known as the subtraction property of equality. And then if you wanted to switch this, you could switch 1 and 2. I kind of wished I had switched it earlier, but that's okay. If you wanted to include the next step to switch them, that's perfectly fine. That would be a symmetric property. Symmetric property is, when you switch them, A equals B, B equals A. So that's basically what we're referring to when we refer to that. But again, you can switch them and not refer to the symmetric property. That's perfectly fine. I'm just going to include it here just to include it. And so now we know that angle 1 and angle 2 have to be congruent. And so because we know that they're equal, that means they have to be congruent. And because they're congruent, that means we proved it. But the reason for that is that we're using the definition of congruent angles. Congruent angles. All right, and that concludes our proof. We went ahead and proved the statement. Okay, so now the third example is we're not going to prove the alternate exterior angles theorem. That'll be an exercise for you to show, for you to prove. What we're going to do is we're going to look at a specific problem and use the theorems or postulates in order to prove the statement. So we have a diagram, and we want to prove the angle relationship. We want to prove that BAE. So we want to prove, let's use another color. BAE is congruent to BCE. So basically we want to show that those two angles are the same. And they give us that AC is parallel to DF. So we know that these two lines are parallel. We know that BE is perpendicular. This stands for perpendicular. And perpendicular means that they cross at a 90-degree angle. So that means that BE is perpendicular. That's what this symbol is. This symbol is 90 degrees, right angle. And then we know that angle AEB is congruent to angle CEB. Is what they did over here. So these two are actually... Okay, that's all based off our diagram. I'm going to go ahead and erase these details here so that the picture is clear. Again, we know that these are congruent. I want to look for these. We want to prove that those two in green are congruent. We don't know that they're congruent. We want to show that they're congruent. Okay. So first off, we're going to do a 2-column chart. We know that the given statement goes in the first line, right? The number 1. We also know that these are given as well. So I can go ahead and actually just say that I can actually say this. I forgot to include that other statement. Let's just combine them all under one. Okay, and I'll just call this step 2, but that's also given. Now you don't have to give all the statements in the beginning. You can kind of sprinkle them in, but for sure the first one should at least have a given statement. And then if you want to spread it out and use the other statement, the other given statement somewhere else later on, that's perfectly fine. But I'm just going to go ahead and say that they're all given. We know that, and we're going to go ahead and continue with the next steps. Okay, so first off, we know that because we know that BE is perpendicular to DF, that means that they're right angles. Okay, so if that they form a right angle, basically, is what we're trying to say. Okay, so that means that angle BED and angle BEF have to be right angles. So this is a right angle, and then this is a right angle. Okay, and that's the definition of perpendicular. Okay, so we know that angle BED, or BE, yeah, it has to be BED and angle BEF are right angles. And that is the definition of what it means to be perpendicular. And because they're perpendicular and because they're right angles, that means that they're equal to 90 degrees. So we know that the measure of BED, which is the same thing as the measure of BEF, is 90 because they're right angles, right? So we're going to say that this is the definition of right angles. All right, so now we got that out of the way. We're going to say that AED, so let me erase these now. We have AED and AEB, and it probably would help if I have another color here. So I'm going to say that this angle and this angle add up to 90 degrees. That's because this little part and this little part have to add up to the right angle, right, which is the L. And so by angle addition postulate, those two angles have to be equal to each other. So we're going to be writing that down. So we know that AED, so the measure of angle AED plus the measure of AEB have to equal 90. Similarly, CEF has to add up to BEC in order to get the right angle as well. So these two little angles have to add up to 90 degrees as well. So we're going to write that down for our next statement too. And we'll keep it in one statement because they're both the same kind of thing. So we'll also say the measure of angle CEF plus the measure of angle BEC or CEB, same thing, is also equal to 90. And the reason for that is that that's the angle addition postulate. All right, so now we're on to step 6. So now we got the angle addition postulate out of the way. We can use another theorem that we used last in another lesson, known as the congruent complements theorem. So we can say that AED, so let's do another color here, or let's erase this and show you what we're referring to. So we could say that AED is actually the same thing as CEB. So this right here is the same thing as CE. Hold on. I said AEB, not AED. So we know that AEB, apologize, AED is congruent to CEF. There you go, that's the right one. So we know that these two have to be identical by the congruent complements theorem. So we're going to go ahead and say that angle AED is congruent to angle CEF, and then we'll call this the congruent complements theorem. And so let me clarify why we're using the congruent complements theorem here, just to kind of shed some light on it. So to kind of refresh our memory on that, congruent complements theorem states that if you have two angles that are complementary to a specific angle, then that means that they have to be equal to each other. So in this case, AED and CEF are both complementary to BEC, to this angle BEC. They're also both complementary to AEB as well. And so if you know that they're complementary to the same angle, and we know that they both are complementary to these angles because these two angles are the same, right? According to the diagram, that's a given. So because they're both complementary to either one of those angles, that means they have to be equal to each other by the congruent complements theorem. So I just want to clarify that. So now we know that they're equal to each other, or they're congruent to each other by the complements theorem. So let me give us some more room here. And so now what we're going to say is the angle. Now we're going to look at some angles here for the alternate interiors angle. So if you look at let me erase this so we can focus on what I'm pointing out here. So if you look at BAE and AED, these two angles here, those are alternate interior angles because you have two parallel lines cut by a transversal. In this case, the transversal is this line right here. So we're going to use the theorem that we were proving earlier, right? The alternate interior angles theorem. In order to show that, well, these two angles in black are both equal to each other. So angle BAE is congruent to angle AED. Similarly, if you look at BCE, this is congruent to CEF. Those are also alternate interior angles, right? If you think of this as being your transversal, well then those are both inside the sandwich, and they alternate on both sides of the transversal in green, and so they're alternate interior angles, which means they have to be equal to each other. And so we're going to say that angle BCE is also congruent to angle CEF. And the reason for that is that we're using the alternate interior angles theorem. All right, so where are we going with this? Well, for step 8, we can go ahead and say, well, so we can go ahead and say that, well, we know that, I'll be careful with the color here. We know that BAE is congruent to AED, right? And BCE is congruent to CEF. But we know that AED is congruent to CEF by statement 6 right here. So these two are equal to each other. And so these two are equal to each other right here then. And that means that, well, then that means that these two have to be equal to each other. They have to be congruent, rather. And that's known as the transitive property, right? So we're using the transitive property of congruence in this case to show that they're the same. So here, I'm going to say, change the color here. I'm going to use a transitive property. Not a transitive property of equality. We're using congruent statements here. So this is actually a transitive property of congruence, not of equality. But we know that they're very similar concepts here. So we're going to go ahead and say, this should be, let me go and double check the wording here. Okay, so so then we'll go ahead and write the statement. Have angle BAE has to be congruent to angle BCE. And remember that that's actually what we were trying to prove. We were trying to prove that BAE is congruent to BCE. And so therefore the proof is completed. All right, guys, that is going to be it for the lesson, the examples for this lesson. I hope you learned a few things. Again, this was mostly about proofs. And then the first part was about actually using angle pairs and answering those kind of questions with specific angle measures. I hope you took something from this video, and I'll see you in the next one.